When you write a query in SQL, you just hit enter and then rows come back. But between those two moments, the database actually does six distinct things. And it's within those six things that almost every performance problem you've ever experienced lives inside of. And so that's what this video is going to be about, talking about the inner workings, the parser, binder, rewriter, optimizer, executor, and the piece at the end that hands you your rows when you actually write a SQL query. So I'm going to walk the entire path your SQL query takes. And then I'm going to show you, hey, how do you know which stage something is slow is? So next time something's slow, how do you identify which stage it actually broke in? And why I did this is because almost every SQL, all SQL tuning out advice out there is, just kind of like a cargo cult where you have, add an index, avoid select all, never use a subquery. And some of that is right some of the time, and none of it tells you why you actually did those things, right? And so what I want to do is, basically say a different type of sentence, right? Something like the optimizer picked a nested loop because it underestimated the outer side by 50 times, and it underestimated because the statistics in this column are 3 weeks stale, right? You can fix that sentence because it identifies a real problem. It's not just, hey, the query is slow, I'll try an index, I'll try something else until it actually works. So that's what this video is going to be all about, right? And so if you already read plans, but you've never been sure about what those estimated numbers mean or why they go wrong, you can skip along later in the video. And by the end of this, you're going to have a 4-step process you can run on any slow query in any SQL engine. And I'm going to be talking about all this in Postgres because its planner is really well documented and its plan output is the most readable of anything out there. But if you're on Snowflake, BigQuery, or some of Spark, your plans can use different words, but you're still going to be hunting for the same underlying things, right? And so the query I'm going to be using for most of this video is a very boring one, just a select statement where sign up date is greater than 2024 January 1st, status is shipped, and I'm grouping by customer ID and customer name. And that's going to give me two tables, right? Customers, let's say, has around 200,000 rows. Orders has about 12 million. Nothing clever. And this query can take 80 milliseconds or it can take 40 seconds without changing a single character of it with the same SQL and same schema and same indexes. All we have to change is what the database actually believes about the data. So stage one, parse, is going to be turning that text into a tree, right? Checking the grammar and nothing else. Stage two is binding, which is resolving every name in that tree against the system catalog. So customer stops being a string, becomes an actual table. Then stage three, rewrite, so expanded views, flattening some subqueries, inline CTEs to find that data. Step four, plan and optimize, generate the possible ways to run the query and then pick one. And then stage five, execute, run the plan. And then stage six, return, handing the rows back to you. And a lot of pain you're going to experience is going to be within this stage four, right, where planning and optimize the different ways to answer the query and pick one. And that's where most of this video is going to talk about, right? But these earlier stages also explain a whole category of confusing errors as well. So we'll start at the top with parsing and binding. So starting at the top, parsing is the stage where the database turns your SQL text into a tree. It's going to check grammar only, and it doesn't know your tables exist, it doesn't know your columns exist, and it also just doesn't care. And then the output of this stage is a parse tree, sometimes called an abstract syntax tree, where you have nodes for the select list, the from clause, the where clause, the join condition. And at this point, customers is just a string sitting in a node labeled range table entry, and the parser has no idea whether that's a real table. It's just figuring out what does this SQL statement mean. Then comes binding, which is sometimes called name resolution or semantic analysis, right? And this is where the database goes to the system catalog and asks, does a table called customers exist in the search path? Does it have a column named sign up date? What type is that column? Does the current user actually have permission to read that column? And then every identifier in your query gets resolved to an actual object ID, and every expression gets a type. And the split that is, that part of the split that matters is that two errors that feel identical to you can come from completely different stages, right? Let's say I write a bad select statement where I, leave the E out of select, right? That's the parser. It died on grammar and it never looked at your database at all. And you could have typed that against an empty database with no tables and gotten the same message. But if you make a similar spelling error in customer and type in, forget the O in customer, right? The grammar was fine, and that's the binder that's actually failing, because select identifier from identifier is a perfectly legal sentence to the parser because it doesn't care about if that table actually exists. It's only going to fall over when the database went looking for that column in the catalog and then it came back empty. And the reason you should care is because it'll explain a whole class of confusing behavior, like why Postgres sometimes reports a syntax error at a position that seems unrelated to your actual mistake. That's the parser giving up at the first token it couldn't fit into the grammar, which is often several tokens after the real problem. So if you ever wonder why a query in a stored procedure passes at creation time but blows up when you run it, depends on the engine, but it's usually because binding got deferred. And then one that really will bite you in production is that if you drop or recreate a table or change a column type, the text of your query hasn't changed, but the binding result has. Cache plans have to be invalidated, and if the engine gets that wrong, or if you're using prepared statements with a plan cache, you can get errors that look like a database has lost its mind, but it hasn't. It's holding onto a binding from a schema that no longer exists. And then binding also does something subtle that will matter later, in that it decides types, and types decide what operations are legal, and then that constrains what the optimizer is allowed to do. So if sign up date is a text column instead of a date, that comparison to 2024-0101 becomes a string comparison, and a whole set of index and range optimizations will quietly become unavailable. So the query will still run, but it's just slow forever, and then nothing in the error output tells you. And it's a very real thing, right, where someone can load a CSV, every column arrives at text, and then the query will work fine, but 6 months later it can be the slowest thing in the warehouse, right? So parsing and binding are the stages that will produce very clear errors, though, because they're either going to work or they shout at you. The next stage is where you start getting into kind of the silent failure errors, and where we're going to spend a little bit more time going into the weeds. So the next step is the optimizer, and the optimizer will be picking between logically equivalent plans by estimating how expensive each one would be, and it'll make those estimates using the statistics about your data. So everything else in this section is me just really going into the weeds on that sentence. So logically equivalent means that plans that return exactly the same rows. Right, so for my query, the database could scan customers first and look up matching orders, or it could scan orders first and look up matching customers, or it could scan both and fully and hash them together, right? And it'll give me the same answer every time, but with wildly different runtimes. And so before the optimizer gets there, one stage I skipped was the rewriter, right? And that's where the views get expanded into their underlying queries. Some subqueries get flattened into joins, and where in modern Postgres, a plain CTE will get inlined into the main query instead of being materialized separately. That was changed in Postgres 12. And because before 12, CTE was kind of an optimization fence, and people use with deliberately to stop my optimizer from touching a subquery. Now you have to write with as materialized to get that behavior back. So just keep that in mind. And so now the optimizer, right, it generates candidate plans, then assigns each one a cost, right? And cost is a unitless number. It's not milliseconds. In Postgres, cost 1.0 is essentially defined as the cost of reading one page sequentially from disk, and then everything else is priced relative to that. So, the price list for something like this would be show sequential page cost, 1, show random page cost, 4, show me a CPU tuple cost, 0.01, right? And so on and so forth. So Postgres will believe, hey, random page read is 4 times more expensive than a sequential run because I'm going to have to figure out what that page is. And then processing a row in a memory is going to cost about 1/100th of a page read. And on spinning disks, that 4.0 is roughly right. But if you're using something like NVMe, it's actually very wrong, right? And if you're on decent SSDs and you never touch random page cost, your optimizer is going to be systematically biased against index scans. So dropping these values to 1.1 or 1.5 is one of the few knobs you actually can tune without really a specific diagnosis behind it, because it's just making use of better hardware. And then the cost model is the less interesting half. All right, the cost model is just roughly constant. The part that'll change underneath you is the statistics, right? So if you run something like select all from or attribute name, distinct, fraction, correlation from PG stats, and to get all this information on your stats, right? N distinct is going to be your estimated number of distinct values in a column, and when it's negative, it means that a ratio it's a ratio to the table size. So -1 means every value is unique, and then most common values and most common frequencies will hold the top values and how often they appear, which is how the planner knows that status ship matches 60% of orders while status refund matches 0.4%. And then histogram bounds holds evenly spaced buckets for everything that isn't in the most common list, which is how range predicates get estimated. And then correlation measures how well the physical row order on disk matches the sort order of that column, which is how the planner actually decides on whether an index scan will be doing sequential reads or bouncing all over the disk. So if you were to do something like run explain on a query with fresh stats, where you get a hash join estimated 4.2 million rows out of orders, and it's going to run at around 900 milliseconds. It's a reasonable plan for a big join. But let's say you load a new batch of data and you don't run analyze, where same query, same schema, same indexes, and then if you look at the plan, right, you'll get a nested loop, estimated 900 rows on the other side where I'm looking for 3.1 million, and the planner thought it was looking up a few hundred customers, so a nested loop looked cheap, but it's actually doing 3 million index lookups in 40 seconds. And nothing about the queries changing, right? Again, this database's beliefs changed and the plan followed beliefs, and all this is just from adding analyze orders to the end of a query, right? And so if a query was fast last week and it's slow today, nobody deployed anything, this is where you want to look first, right? Stale statistics. In Postgres, auto vacuum triggers and analyze when roughly 10% of the table has changed since the last one, plus a small constant. So on a 12 million row table, that's 1.2 million rows of churn before the planner updates its worldview. And so if you bulk load, you'll have a table with a strong time skew where all the new rows share a value that didn't exist at the last analyze. Or if you're querying a table right after an ETL run, you're querying with a stale map. In the fix, again, boring, just run analyze after bulk loads as an explicit step in your pipeline rather than hoping or waiting for auto vacuum. And so the optimizer, again, isn't being clever here and isn't being stupid either. It's just doing arithmetic on numbers you handed it. So if you have the wrong numbers here, perfect arithmetic, but you're going to get garbage out. And the arithmetic underneath the hood, getting to that now, mostly spends time choosing between three specific things. So now let's go and look at those. So what are those three things? There are three join algorithms that will show up in almost every relational engine. There's the nested loop, hash join, and merge join. So the optimizer will pick one per join based on the estimated row counts, what indexes exist, whether the data is already sorted, and how much memory it thinks it can use. So you start with the nested loop. For every row on the outer side, go and find the matching rows on the inner side. If the inner side has an index on the join key, each of those lookups is cheap, and the total cost is roughly the number of outer rows times the cost of one lookup. So nested loop wins when the outer side is small, genuinely small, like hundreds or low thousands of rows, and there's an index on the inner join column. And it's also the only algorithm that works for non-equality joins because you can't hash a greater than condition. If you write a range join, you're getting a nested loop, whether you like it or not. And nested loop will lose catastrophically when the estimate on the outer side is too low. That's that 40-second plan from the last section, right? Cost scales linearly with outer rows, so 1,000 times estimate error gives you 1,000 times the runtime. Every other algorithm will degrade more gracefully than this one. So when you see a slow plan, this is what the damage usually is. And second one, the hash join. So pick the smaller side, read all of it into the memory, and then build a hash table keyed on the join column. That's how the hash join works. Then you stream the bigger side past it and probe the hash table once per row. And hash join is the workhorse for large equality joins where you read each side once. Cost is roughly linear in the total rows on both sides, so it doesn't blow up when the estimate is off by 10x. And the catch is memory. If the build side doesn't fit in working memory, Postgres will partition it and spill batches to disk, and then your plan will sprout a line like batches 65,000, batches 32, memory usage 4K kilobytes, and batches greater than 1 usually means that it's spilled, right? And that's a real slowdown, and it's a legible symbol that you can see on a load, so look for that. And then also hash join only works on equality. On a.x equals b.y gets a hash join. On a.x between b.low and b.high does not, as you can't have that kind of range there. And then third, you have the merge join, where you're sorting both sides on the join key, then walking them down together the way you'd merge two sorted lists by hand. So every side gets read once, there's no hash table, and memory usage stays flat no matter how big the inputs get. And merge join wins when the data is already sorted because let's say you're reading it off of a B tree index in key order, or because a sort was needed anyway for order by upstream. If the planner has to add sorts on both sides just to enable it, hash join usually wins instead. And merge join is also the one that handles very large joins without memory pressure, which is why it shows up more in engines and workloads where memory is tight. And so making this tangible, right, as let's say you had set enable hash join off and then did explain analyze select, right? It's going to add a huge penalty cost, so the planner will avoid it if anything else is possible. And so with hash join, then the estimated cost will be 184,000, actual 940 milliseconds, forced onto a merge join, right? Estimated cost 511,000, 6.2 seconds to complete. And the planner was right there. The ratio predicted, roughly 2.8x, wasn't far off the 6.6x it actually will get, but the estimate isn't perfect, but the ranking was correct, right? And the ranking is all the optimizer needs to get it right. So it knows to do a hash join instead of that, even if the ratio of performance gain isn't actually that much better, right? And what this tells you about something that the optimizer is actually for, right? It doesn't need accurate costs. It just needs the cheapest plan to come out cheapest. And so it manages that when the row estimates are good, and it'll fail at that when they aren't, which means that every time you're looking at a bad plan, you're looking at a bad estimate. So let's go look at some estimates. So here is an actual query plan kind of visualized here for you. So an explain analyze plan is a tree, and you read it actually inside out, where the most indented lines run first and the results feed upward into their parents. So every line has an estimate from the planner and an actual measurement from the run, and the whole skill is then comparing those two numbers. So if you have this kind of query up on the screen, group by, and you read it inside out, right, where the deepest nodes are the sequential scan on customers and then the index scan on orders, those will run first, and then they feed the nested loop, which feeds the sort, which feeds the group aggregate at the top. So the four numbers in every line is, cost A to B is two numbers, not a range. A is the estimated startup cost, the work before the first row can come out. B is the estimated total cost for all rows. For a sequential scan, startup is near zero because the rows come out immediately. But for a sort, startup is high because a sort can't emit anything until it has seen everything. And that's why sorts and hash aggregates are called blocking operators, and why they're the nodes that make a query slow to return its first row, even when the total throughput is fine. Then rows equal is the estimate. And then actual rows equal is the truth. And this comparison is very important because it's going to tell you, hey, what is the actual true amount of rows you need to use? And then loops is how many times the node ran. And the trap that will catch people is that in Postgres, actual rows and actual time on a node are averages per loop, not totals. So if you look at an index scanner and it says rows equals 64, loops equals 48,000, it's not 64 rows, that's 64 rows on average 48,000 times, which is 3.1 million rows, and time 0.007 milliseconds looks instant until you multiply it by 48,000, and then you get 340 milliseconds. So you got to multiply all those numbers out before you judge. And then three big red flags to look at are, number one, a large gap between estimated and actual rows at the deepest node where that gap first appears. So in this plan, sequential scan on customers estimated 902 and it got 48,000. That's a 53 times underestimate, and then everything above it is going to inherit that error. And then the nested loop estimated 1,000 rows and produced 3.1 million, right? So the planner didn't make a second mistake there, it just made one mistake at the bottom and propagated it up. So you always find the deepest node where the estimate goes wrong, because everything above that is just a symptom of that first failure. And so here it's a sign up date filter, which means the stats on sign up date didn't reflect the data, which means someone bulk loaded and didn't analyze. And then red flag 2 is anything spilling to disk, right? So here's that sort method, external merge disk, 141,000 kilobytes, right? That sort wanted 138 megabytes, and working memory didn't give it that, so it went to disk. And the same thing for hash joins with batches greater than 1. And that's fixable by just raising working memory for the session. But then you also want to notice the ordering, right? It's spilling because it's sorting 3.1 million rows it shouldn't have had in the first place. So again, fix the estimate, spill disappears on its own. Don't treat the system. And then red flag 3 is a nested loop with a big loops count, 48,000 of them here. And that's the shape of a plan that shows nested loop based on a small estimate and then got a large reality. When you see loops in the tens of thousands and up, look immediately at whether the outer side estimate was right. And then a couple things I always like to add are explain, analyze buffers, gives you shared hit versus shared read per node, which tells you what came from cache and what came from disk. And a plan that looks fine on a warm cache can be a disaster cold. And then rows removed by filter tells you how much work got thrown away. So that sequential scan that read 200,000 rows and discarded 150,000 of them, that's the argument for an index on sign up date, and it's a much better argument than add an index. It's always faster. And that's everything, right? So that all the different plans it's going to be reading through to try and or everything it's going to read through to figure out an actual query plan, right? So then at least one question, which is if everything's doing the same job, why does the same query fly in one and then crawl in another? So the real underlying reason that the same query can run at different speeds in different databases or in different engines is because the execution engines themselves process rows in fundamentally different units. One row at a time, a batch of column values at a time, or a partition at a time across a network. And that difference is what will decide which engine is fastest for which query, so make sure you're choosing the engine that's right for your actual database provider, right? And the three models kind of worth knowing is, obviously first row-based, tuple at a time. This is classic Postgres. The executor is a tree of operators, and each one has a give me the next row function. So the top node asks its child for a row, which asks its child all the way down, one row at a time, and this is called the volcano model. So the the overhead is a function called per row per operator. So a query touching 50 million rows pays that overhead 50 million times over. And so what this is good at is fetching a few rows by key, high concurrency OLTP, anything where you touch a tiny fraction of the table, but it's bad at scanning 40 million rows to compute one average. The second model is columnar and vectorized. This is what DuckDB, ClickHouse, Snowflake, and BigQuery and columnar file formats like Parquet live. And columnar storage means values for one column sit contiguously on disk. So if your query touches 3 columns out of 60, you read 3 columns worth of bytes. Row storage would have made you read whole rows to get any part of them, and because a column holds one type with often repetitive values, it also compresses far better, so you're reading fewer bytes on top of reading fewer columns. Vectorized execution means operators process a batch of values at a time rather than one. DuckDB's batch is 2048 values, and instead of a function call per row, you then get a function call every 2048 rows, where the inner loop is a tight loop over an array with no branching, and the CPU can use SIMD instructions to do several comparison per cycles, so the per row overhead basically will vanish. And that's the reason that DuckDB can embarrass Postgres in analytical scans. It's nothing to do with the optimizer being smarter, it's just a better fit between how data sits on disk and what the query needs to touch. Then the flip side is just as real, right? Point lookups and single row updates in a columnar engine are miserable because touching one row means visiting each column's storage separately, which is why no one's running their checkout flow on something like DuckDB. And the third model is distributed with a shuffle. Spark, Trino, Snowflake at scale, BigQuery, where data lives on many machines, and a join needs matching keys on the same machine, so rows get hashed from the join key and then sent across the network. And that's a shuffle, and it's the dominant cost in almost every slow distributed query. So 2 things to know is that first, if one side of a join is small, the engine broadcasts it, sending a full copy to every node, so no shuffle is needed for the big side. Broadcast versus shuffle is the most consequential decision a distributed planner will make, and it's based on the estimated size of the small side. So if that estimate is wrong, you either broadcast something huge and blow up executor memory, or you shuffle something tiny for no reason. Then second, you have skew. If 40% of your rows have the same join key, they all hash to the same node, so one task runs for 20 minutes while 199 tasks finish in 10 seconds. Your cluster can be 99.5% idle and your query is still running, and skew is invisible in the average and obvious in the max task iteration, which is why you look at task distribution and not at totals. So a query that flies in DuckDB and crawls in Postgres is almost always a full scan aggregation where columnar plus vectorization wins, and a query that flies in Postgres and crawls in Spark is almost always a small selective lookup where the distributed engine fixed overhead dwarfs the actual work. Neither engine is better, they're just built around different assumptions about what you're going to ask, so match the engine to the access pattern before you tune anything else. Someone that's optimizing an analytical query that could have run in 2 seconds in DuckDB is just doing the wrong kind of work, right? You just got to switch the actual underlying engine. So now that I've given you all the nitty-gritty on how queries actually work under the hood, what is a checklist you can use to actually figure out what's wrong with a query and stop as soon as you find the problem, right? So if you do these steps in order, you just stop when you find the problem, you'll see it pretty easily, right? So step 1, check the statistics before you touch the query at all. When did this table last get analyzed, right? If nmod since analyzes a meaningful fraction of nlive tup or last analyze is older than your last big load, run analyze and retime the query before doing anything else, because a third of sudden mystery slowdowns are probably just because you haven't done that analyze in a while. Step 2, get the plan with explain. And not just plain explain, but explain analyze buffers, right? Because plain explain will hand you estimates, and estimates are the thing that you currently suspect of lying, so you need the actuals to hold them against. Then step 3, find the deepest node where estimated and actual rows diverge. Not the slowest node, but the deepest wrong one, right? The one that the first error occurs, because the slowest node is just a downstream victim of that bad estimate. So find the first lie and the rest of the page will start making sense. Then you multiply by loops before you judge anything. Then step 4, choose between an index, a rewrite, or a different engine. Those are 3 real options, and each one will answer a different diagnoses. An index is right when the scan is reading a lot and discarding most of it. Rows removed by filter is large relative to rows returned, and a filter is selective. That's a genuine index case, right, instead of a reflex of adding one because the query is slow. A rewrite is the right move when the optimizer is being blocked from better plans. So if you have something like a function wrapped around an index column so the index can't be used. An implicit typecast would be doing the same thing, or a correlated subquery that would be faster as a join, and or across 2 columns that would be faster as a union all. And all of those, the optimizer could do better, and your SQL is preventing it from doing that. So you got to change your SQL. And then a different engine is right when the access pattern doesn't match the storage model. Full table aggregation on a row store, single row lookups on a column store, small selective query on a distributed cluster. No amount of tuning fixes an architecture mismatch, and recognizing one early will save you a ton of time. And a caveat there is, some engines let you force a join type or an index. Do it to diagnose the same way I forced a merge join earlier, then take the hint back out, because a hint in production code is a permanent bet that today's data distribution will hold forever, but it won't. And when it stops holding, the hint prevents the optimizer from adapting. So hints can turn a temporary problem into a permanent one. So now to recap, right? You've got 6 stages between hitting enter and getting rows: parse, bind, rewrite, plan, and optimize, execute, return. Parsing checks grammar. Binding resolves names against the catalog, which is why a syntax error and column does not exist error come from different places. The optimizer picks among logically equivalent plans by estimating costs from table statistics, and stale statistics are the most common cause of a query that was fast last week and is slow today. Then there are 3 join algorithms: nested loop for a small outer side with an index inner side, hash join for large equality joins, merge join for data that's already sorted. Nested loop is the one that degrades catastrophically on a bad estimate. So read a plan inside out, compare estimated rows to actual rows, and multiply by loops. The 3 red flags are large estimate versus actual gap at the deepest node, anything spilling to disk, and a nested loop with a huge loop count. And the same query will behave differently across engines because of execution model, row at a time versus vectorized columnar versus distributed shuffle, not because one optimized is smarter. So check the stats, read the plan, find the row estimate mismatch, then pick your fix, 4 steps, and you're diagnosing instead of guessing. So I hope you enjoyed this video. I hope you learned something, and I hope you have a great rest of your day. Data Guy out.